we discussed how can we build a model to predict housing prices in California using California census data, right? Okay. So for that,
Hey, Praveen, to interrupt here.
yes,
But can we have a quick review? I, for reasons, missed out on yesterday class. Quick recap, like 2-3 minutes recap would help.
yes,
And I
yes.
was trying to look into the video, like the learning video for yesterday. It's not yet available.
Okay.
So, yeah.
So here we are building a model, machine learning model, to predict housing prices in California using California census data, right? So data we are already given, and here our goal is to predict the house price, right? So here we are first plotting our data so that we can gain some insight from data itself. So here we are using two features or two variables that are given in the data, latitude and longitude, right? Yes, so this data is already given, and using this data, our goal is to predict median house price, right?
Yep.
Yes. So this value we want to predict, and these values are given, already given, right? Latitude, longitude, and medium income, like that. So we have several other values that are given, and our goal is to predict this value, median house value, right? And if you see this data, there are total, I think, more than 20,000 data points are there. Yes. So more than 20,000 data points are given. And these are the value for these variables, right? So for example, this is the latitude, this is the longitude, right? Okay.
Yep.
Yes. Yes. So here we are first visualizing our data. So let's say for a particular latitude and longitude, the circle denotes the district. One district you can assume, right? So within this circle, we have some population, and we want to predict median house price within this circle, within this blob, right? And here blob represent the population, right? So if circle is smaller, which means population is less. If circle is big, which means uh, radius is, let's say, large, then blob will be large and the population will be more, right? So here the size of circle means the population, right? And this color represents the house value, right? So blue color means house is cheap, and red color means house is costly, right?
Mm-hmm.
Yes. Any doubt?
Mm,
Okay.
not really, but like, what is the source of the data that we have gathered it up? Is that one of the prerequisites kind of handled to given to us to start?
Yes, yes. So I already gave the link in yesterday session. So this
Okay.
data is about California census data 1990, right? So this data is already available.
Mhm.
Okay, so previous session we discussed that uh, we are solving a regression problem, right? Because we want to predict a real valued number, right? So here, let's say if we want to predict the housing price for a particular circle, or let's say for a particular district, then if you can visualize the data, we are having these many features, right? Now, can you tell me which feature is our output feature or output, and what variables are the input variables here?
Input variable
The
could be a
output
room.
Yes,
output would be the median house price,
value.
right?
Yes,
Yeah,
exactly.
value.
So this
And
is
rest all
the
will be input.
input variables, right? So only this variable is the output variable, and all other remaining variables are the input variables, right? So for example, this latitude is input, longitude is input, right? Total rooms are total number of rooms within one district or within one circle is again a input variable, right? Okay. So are we solving a supervised problem or unsupervised learning problem?
It's supervised.
Yes. Why supervised?
You have the label.
Yes, we have the label, right? Because here output is median house price, right? And for every circle or for every district, we are having associated house value, right? Median house value. So therefore, we are solving a supervised learning problem, right? Because labels are given, right? Okay. Yes. Yes. So here, in this problem, we are doing supervised learning because label data, we already have the label data, right? And we are solving a regression task, right? Because we are predicting a real valued output, right? Okay. And since we already have all data, so therefore we are using here batch learning, right? Because so all 20,000 data 20,000 data points are already available with us, so we can do the batch learning, right? If data is available partially, then we can do the online learning, right? We can use the online learning technique. But since here the complete data is available with us, so therefore here we will do the batch learning, right? Okay, so I have already discussed these 3 points in previous session, right? So now we will start from performance measure, right? So now what we will do, we will train a machine learning model using the available data, right? So this data we already have. So we will use this data to train a machine learning model, right? Okay. Now, here the question is, how can I verify whether my model is working fine or no? So, to do that, I need performance measure, right? So, I will use some performance measure to measure the performance of machine learning model, right? Now, to measure the performance of any machine learning model, we have to use some performance metrics, right? So the performance metrics can be the square error, can be the absolute error, right? And there it also depends on the task, right? So for example, if we are doing a regression task, if we are predicting a real valued output, then we can take absolute error, square error, right? But let's say if we are doing a classification task, then there are different sets of error functions that we can use, right? Okay, so since here we are doing a regression task, so here we are using a mean square error, right? Okay, so here what do I mean by mean square error? Okay, so here let me go to that slide. Yes. Okay. So now, for the sake of simplicity, assume we are predicting house price based on area, house area, right? And here house area, um, we are house area is given in the square feet, right? Okay. So for the sake of simplicity, assume we are only given one features, one variable, right? But in fact, if you see the original data set, there are several features available, several input variables we are having, right? But for the sake of simplicity, assume we are only having one input, house area, and we want to predict house price, right? So here input is house area, which is given in square feet, and output is house price, right? And since we are doing regression, so that's why we are interested in learning a mapping that exists between input and output, right? Because given some inputs in regression, we will predict a real valued output, right? So we can predict a real valued output for any given inputs when we have that input to output mapping, right? Input to output relationship, right? So here our goal is to learn that relationship, right? So that for any given input, we can predict the output, right? Okay. So for that, here we are using linear regression. Linear regression means we will solve this regression task using linear model, right? Now the regression can be linear regression, can be non-linear regression. If you are using a non-linear model, then we are doing a non-linear regression, right? So what are the example of linear regression? So yeah, I think in previous session I gave some example. Okay, so let me again. Yes. Yes, so I already covered this part, right? In supervised learning, we are given label data and we are learning from label data. And examples are the classification and regression, right? Regression, our goal is to predict real valued output. In classification, model will give us one particular category, right? So we are having some finite categories, and our goal is to predict one category for any given input, right? Okay. And if we are only having unlabeled data, labels are not available with us, then we can do clustering. Clustering is a unsupervised learning problem, dimensional reduction, a unsupervised learning problem, right? And this workflow I have already discussed in yesterday class, right? So if label data is given are available with us, which means here the input are the images, right? Cat images and dog images. So input are nothing but the bunch of dog images, bunch of cat images, and these values are the label, right? So for example, this particular image is a dog image, this particular image is a cat image, so this cat is nothing but the label output, right? Here this dog is the output, right? So since we are given a label data, so in the first step we will extract feature, right? Feature from using these raw input, right? So images are nothing but the raw input. So in first step, we will extract features, and feature is nothing but a vector, a numerical representation, right? A vector of values, right? So for this particular image, we will get one vector of some values, or we will get one numerical representation corresponding to this particular image dog, right? Now, machine learning algorithm or machine learning model can only understand these numerical representation, these vectors. So we will pass these vectors, these numerical representation as an input to our any machine learning model, right? And then machine learning model will will learn some linear model or non-linear model depending on what type of machine learning model we are using, right? If we are using a linear machine learning model, then it will learn some linear model. If we are learning a non-linear machine learning model, then it will learn some non-linear boundary, right? So here, since as you can see, we are learning a linear model, so therefore we are getting a linear separator, linear line, right? That can separate out uh, these two types of data, right? So one side we are having dog images, other side we are having all cat images, right? So using this linear separator, we can separate out dog images versus cat images, right? Okay. Now what we will do at the test time, for any given test image, or let's say this image is available with us, let's say at the test time, then again we will first extract feature, right? We will again first convert the test image into numerical representation, and then we will pass this numerical representation as an input to our machine learning model. And the machine learning model, depending upon which side of this numerical representation or which side of this feature extractor lies. So, for example, if this particular feature lies, let's say, on this side, this particular side, then one particular class. If this lies on this side, then one another class, right? So this way, these machine learning models will work, right? Okay. So any doubt in this workflow? In all supervised learning machine learning models, we will follow the same workflow, right?
One quick question. When you say
Yes,
that
yes.
we will convert the images to vector or numerical format, is there any standard, or we can use anything, and will that have any impact on the output of the model?
Yes, yes, very good question. So yes, there exist several methods. So for example, let's say if you are using deep learning model, in deep learning model, this feature extraction part model will do automatically, right? But if you are using traditional machine learning model, so for example, support vector machine or some other traditional machine learning model, then we have to extract these features manually, and there exist several manual method also, right? So I will discuss very one or two feature extraction methods. But yes, if we are doing deep learning, if we are building a deep learning model, then we don't have to worry about this feature extraction part. It will be automatically taken care by the network itself, model itself, right?
Okay, and for if you're not doing deep learning algo, if you're doing some traditional model, the way we convert these images to features, will that matter in performance of the
Yes, yes,
model?
yes, that matters. Because let's say if this
Okay.
quality of this feature is not good, then obviously the performance of model will be poor, right? The performance of this model or this learning totally depends on the quality of extracted features, right?
Okay.
Okay. In unsupervised learning, since we are not given the label data, we are only having the inputs, we don't have the outputs. So therefore, here we can solve. So see, since labels are not available with us, so therefore we cannot solve classification, we cannot solve regression problem, right? Because to solve the classification problem, to solve the regression problem, we need label data, right? Okay, but then we can solve a few problems. So, for example, clustering we can solve. So, suppose if you want to cluster all dog images in one group, all cat images in another group, then we can solve this type of problem, even if we are not having the label data, right? But then again, we have to follow the same pipelining. In the first step, we will extract features from using these raw images, and then we will pass these feature vectors or these numerical representation as an input to our machine learning model, and then machine learning model will give us the desired clusters, desired groups, right? And how this machine learning model is grouping these images based on similarity, right? So since all cat images share some similar properties, all dog images share some similar property. So based on these similarities, it will group all dog images in one group, all cat images in another group, right? Okay. So this is the pipeline we will follow in unsupervised learning workflow where we don't have the label data, right?
So one question on previous slide.
Yes,
So
yes.
so do we need to feed those property which model can compare each other and then put the images on the different cluster? For
Sorry,
an
can
example,
you? Yes.
so for an example, you are saying cats are having some properties. Similarly, dogs are also having some properties. So do we need to feed those properties to system so that
No. Machine learning model will automatically identify patterns present in the data. So it will automatically find out the similarity that are present in our data, right?
Okay.
Because in ML models, if we are hard coding these rules, then so this is not the purpose of machine learning model, right? Because
Right.
in because the same approach we will follow in rule driven based approaches, right? Where we have several rules, so where we may have several if and else statement. If this condition is true, then do this, else do this, right? So that type of setup is called the rule driven based, right? And here this machine learning setup based on the data driven, right? It is data driven. So based on our data we will learn pattern, and using those patterns model will predict at the test time, right? So we will not we don't have to worry about the similarity. Model will automatically learn the similarity, right?
Uh, I just have one doubt. So,
Yes, yes.
this images when you are giving,
Mhm.
we make the embeddings of that, like
Yes,
embedding
yes,
embedded vectors.
yes, yes.
And what is this feature extraction, and what like how
No,
is the feature extraction and embedding?
embedding you can think like this vector only, right? Because in embedding also we are getting a vector of some values, right?
Okay, so feature extraction and the embeddings are similar, right?
Yes,
I am
yes.
just confused. What is this
Mhm,
feature
mhm.
extraction? What is this embeddings of?
No, 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 both are same.
Okay.
So embedding we generally use in NLP terms, right? Here in machine learning, deep learning, we use the term features, right?
Okay. Okay.
Okay, then I also discuss these supervised and unsupervised learning problems from geometric perspectives, right? So in regression, what exactly we are doing? We are trying to establish some relationship between input and outputs, right? So Y is here the output, X is the input, and we are establishing some either linear or non-linear relationship between input and output, right? So in regression, given some inputs, we are predicting a real valued output, right? So in all regression problem, we will do the same. We are given some inputs, and our goal is to predict a real valued output. And this real valued output we can only predict when we know this relationship, input to output relationship, right? And this relationship can be linear, can be non-linear. So for example, in this case, relationship is linear because we are learning here one line, right? Okay. Now this relationship can also be non-linear. So here we are learning a polynomial. So therefore, this relationship is a non-linear relationship, right? So here we are learning a non-linear model. Here we are learning a linear model, right? Both are both are the example of regression problem, right? In both cases, we are predicting a real valued output given inputs, right? So regression from geometric perspective, you can think like a line or curve fitting problem, right? Here, in this case, we are fitting a line, and in this case, we are fitting a curve, right? So in 2D, uh, we will fit a line. In 3D, we will fit a plane, right? In 2D, we will fit a line. In 3D, we will fit a plane. And let's say if you go beyond 3D, then we will fit a hyperplane, right? So line, plane, and hyperplane depending upon the number of inputs, right? Okay. In the classification problem, our goal is to learn a model that can predict which of the two or more classes an input belongs to, right? So input may belongs to some finite number of classes. So in classification problem, we are given some finite number of classes, and our goal is to predict the correct class for any given input, right? Now here in this case, the model will learn a separator. That separator can be a linear separator, can be a non-linear separator. So for example, in this case, in this classification case, the model is learning a linear separator, right? And here in these cases, model is learning a non-linear separators, right? So in classification problem, what exactly we are doing? We are learning a either linear or non-linear separator depending upon what type of model we are learning. If we are using a linear model, then we are learning a linear separator. If we are using a non-linear model, then we are learning a non-linear separator, right? Okay. Yeah, and these are the example of unsupervised learning. So, for example, in clustering, based on similarity, we are grouping inputs, right? So, for example, all these points belongs to one group, all these points belongs to one group, another group, and all these points belongs to the third group, right? Then dimensionality reduction. In dimensionality reduction, again, is unsupervised learning problem. We can solve this problem without any label, right? And here the goal is to compress or reduce the data dimensionality, right? So, for example, if you initially have data in 2D, right? So here you can see each data points having two feature values, two inputs, right? X1 is the first input, X2 is the second input, right? So each data points, each blue points having uh, 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 two features, two variable values, x1 value and x2 values, right? And suppose if you want to reduce this data dimensionality from 2D to 1D, right? So we can reduce data dimensionality from high dimensional to lower dimensional using dimensional reduction techniques, right? Okay. And yes, sometimes we also use data pre-processing techniques, right? Because let's say if we are having some noise in our data, if we are having some outliers in our data, then we have to filter out. Uh, Sometimes we filter out noises present in our data or outliers present in our data. We can do this by using data pre-processing techniques, right? So I will discuss few data pre-processing techniques in the same example, right? Uh, in house price prediction example, we will filter out some outliers, right? Okay, so data pre-processing is technique to clean our data, right? Okay, so let me ask one question. Data pre-processing, how do I know whether I should use some data pre-processing techniques or not?
Can you repeat the question?
Yes, yes. So yes. So it's not like that we always use the data pre-processing techniques, right? Depending upon our requirement, we may use data pre-processing techniques and we may not use the data pre-processing. The question is, how do I know that we have to use some data pre-processing technique to solve some particular problem, right?
That depends on multiple factors, right? Whether your data is synthetic or non-synthetic.
Yes,
Whether
yes, yes.
what's the classification of the data? Is it carrying sensitive or not? So based on those, I mean, there are multiple variables, right, to think of
Yes, yes,
to,
yes. So,
to
so
decide
we,
on the piece.
yes, yes. So, in fact, we don't have answer for this question. It depends on several factors. So, for example, let's say if you can visualize your data, and by visualizing your data, you can easily say that in our data we are having some noise, some outliers pixels are there. Then we should use the data pre-processing technique, right? And as you said. When we are making let's say some synthetic data, so synthetic data is again not the actual one, so therefore we have to use the data pre-processing techniques so that we can clean our data, right? Yes. Now
Yep.
let me yes. So now let me quickly discuss the techniques using which we can convert raw data to some numerical representation, right? To how can we convert raw data to feature vectors? Yes. So ML algorithm or machine learning model require a numerical representation of each input, right? Because a model cannot directly understand the raw data, and we have to first convert data points to some numerical representation, right? Okay. So here one point I would like to discuss that if we already have our data in numerical form, then we will not do this step. right? We will not do feature representation. We will not extract features because we already have data in form of numerical vectors, right? So if you see this particular example here, we already have data in numerical forms, right? So therefore, we will not extract features, and directly we will use these values as we will pass these values as an input to our machine learning model, right? But let's say if you are dealing with images, then we have to extract, we have to convert image to some vector of values, right? To some numerical representation, right? Yes. So in this case, we will not
We have
extract.
one.
Yes.
We
Yes.
have
Yes.
one value, right? That ocean proximity, that is not a vector. I mean, numerical vector. So we'll have to convert that.
Yes. 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 You are correct. So this we can convert, right? So for example, if let's say this ocean proximity, let's say 4 values are possible, then we can assign, let's say 0, 1, 2, 3, 4 values, right?
Okay.
Yes. Okay. So now let me quickly go through the techniques that we may use to convert raw data to some numerical representation, right? Okay. So here there are two approaches. First approach is we can extract these feature vectors manually from raw input. The second approach is we can learn these features from raw input itself, right? So this second approach is used in deep learning, right? In deep learning models, we will not extract these features manually, and model will do automatically, right? Model will automatically extract features from raw images, raw data, and we will not do this manually, right? But in traditional machine learning models, we have to extract features manually from raw inputs. Then only we can use machine learning models, right? Okay. So now the question is, how can we extract features from raw inputs manually? So it depends on our what type of problem we are solving and what type of data we are dealing with, right? Okay. So let's say if you are having some text data, right? If you are solving a problem using some text data, then you can use bag of word feature representation to convert these inputs to some numerical representation. And what I mean by bag of word? A bag of word is a very simple techniques. Here we will create one dictionary, right? So for example, here I will write the words that we are having in these sentences, right? So for example, Jones likes to watch movies, and then Mary, right? So this way I can create this dictionary, and then I will write here whether this word is present in sentence one or not, right? So for example, John is present, so I will write here one. Likes is present, I will write here one. Two is absent, so I will write here zero, right? So this way I can convert this sentence one into numerical representation, right? And what is the numerical representation corresponding to this sentence one? It is 1111000, right? So this is the numerical representation for sentence one. Similarly, this last row, this third row, is the numerical representation for third sentence, right? So any doubt in this example? And yes, this is just the one technique. There exist several other techniques to get the numerical representation, right? Yes. So in this case, we are converting sentences to some binary vectors, and that binary vector we can use to train our machine learning model, right? Okay. Now let me discuss the methods that we will use when we are dealing with image data, right? Yes. So if we are having image data, we can use flattening technique to convert images into some numerical representation. So for example, let's say if you are having a 7 by 7 image, 7 by 7 image means the width of image is 7 and height of image is 7, right? So there are total 49 pixels in this image, right? 7 is the width and 7 is the height, right? So there are 49 pixels. Now, depending upon what type of images we are using. Let's say if you are using a grayscale image. So in grayscale image, the pixel can have 0 to 255 value, right? Because there are total 256 values. It can any pixel can have in grayscale image, right? Okay. So these pixel values we already have numerical values, right? Now in flattening, what we will do, we will simply flatten this image to convert this vector, right? So vector of size 49 cross 1, right? So this is a vector of 49 cross 1, right? So first row we will arrange in column wise here. The second row we will again arrange the column wise. In this way, we can flatten 7 cross 7 image to a 49 cross 1 vector, right? So this approach, this method is called the flattening method, right? The second approach is histogram. Histogram of visual patterns is another popular technique to extract feature from raw images, right? Now, what we will do in histogram here on the x-axis, we will mark some patterns. So, for example, for this particular image, we are having several patterns. Now, we will count how many times this pattern we are having in this particular image, right? So, this height will tell us the number of times this pattern is having. So, for example, let's assume this height is 50. 50 means this pattern is present 50 times in this particular image, right? This particular pattern, let's say this height is 45. So this pattern is present 45 times in this particular image, right? So likewise, we can count how many times each features are repeating in this particular image, and we can create this histogram. And this histogram we can take as a numerical representation, right? So, for example, this is the pattern 1, pattern 2, pattern 3, pattern 4, and pattern 5. So there are assume you are considering 5 patterns. So you will count here the number of time pattern 1 we are having in this particular image, the number of times we are having this pattern in this image. So, for example, this pattern we are having 50 times, 45 times, let's say 40 times, then again 45 times, and let's say 50. So the numerical vector will be 50, 45, 40, 45, and 50, right? So this is the numerical vector or numerical representation corresponding to this image. So this method is known as histogram of visual patterns, right? And this first method is called the flattening method, right? And in fact, there exist several other methods to extract features manually, especially in computer vision and image processing. Shift feature we can use, histogram of gradient we can use to manually extract features, right? Any doubt in this manual feature extraction?
Why do we need this flattening thing? What is the purpose of flattening this? I didn't get.
Yes. So here we want to convert this image into some vector of values, right? Because model can only understand uh, numerical values, right? So this is why we are converting the image into a vector, right? So here the size of image is 7 by 7, and we are converting this 7 by 7 to some 49 cross 1 vector, right?
No, can't we use a 7 by 7 the metrics? I'm just like,
No. Yes. Okay. So let me again show you this
yeah,
geometrical
I missed
perspective.
yesterday's class. Then maybe that is the problem that I'm not able to.
Yes. So let's say when we are learning a machine learning model, so from geometric perspectives, what we can think that each data points we can represent as a point in high dimensional space, right? So, for example, let's say if input point having if any point data point having two values, right, two variables, two inputs, let's say we are having for all input data points, then each and every data points contain two values, right? So that the data points we can represent as a point in 2D, right? If a point is having, let's say, um, uh, let's say 3 features, then that data point we can represent in as a point in 3D, right? So likewise,
Yes.
you can represent this. Yes. So likewise, you can represent this vector as a point in 49 dimensional space, right? So for example, in 2D we can represent 2D points as a point, right? In 3D we can represent three-dimensional data as a point, right? In 1D we can represent one-dimensional data as a point, right? So likewise, we can represent this 49 dimensional data 49 we can represent this vector as a point in 49 dimensional space, right? Now in that space we are learning a, so let's say if you are if you are doing regression, then we are learning this line or curve, right? So in 3D we are learning a plane, right? Similarly, in classification case, we are learning a linear or non-linear decision boundary. So therefore, we need these values, uh, these input values to be a point in some high dimensional space. Then only we can learn these these
Correct.
separators, right?
Correct. Correct. Yes. Yes.
So how we will extract vectors from the images? How will extract pixels from the images?
Mhm. So in flattening is a very simple approach. We only have to flatten this image, and we will get this vector, right? And if we are doing histogram of visual patterns, then we have to first identify what visual patterns we are interested in, right?
But how we will identify it in the code? In the code, we will identify which pattern
Yes,
will be.
yes. So uh, yes, so for this particular problem, I will discuss the histogram part, right? So here also we are plotting histograms, right? So histograms we can plot using this hist command, right? So I will discuss this part later, right?
Okay.
Okay.
And one more question in the previous, like the dimensionality reduction you mentioned. So why we are doing dimensionality reduction?
Yes, so dimensionality reduction also I will cover in great detail later, right? So because here we are doing supervised, right? So unsupervised we will do after finishing supervised learning part, right? And yes, dimensionality reduction sometimes. So let's say if you want to compress your data, right? So then you can do the dimensionality reduction, right? So let's say if you are having limited space, then you can compress your data to save space. And the other use case can be let's say originally you are having 100 inputs, 100 values you are having, and if you use all 100 100 input values, then and if you train any machine learning model, then it will take some time to give you output, right? But let's say somehow if you filter out if you can compress from 100 to 10, then if you learn any machine learning model, it will be much fast, it will work much fast, right? So there are the cases where we use dimensional reduction, right? So first use case is when we want to compress our data. The second use case is when we want to filter out spurious features, spurious values that are present in our data, right? So for that also we will do the dimensional reduction, right? Or let's say if you want to speed up your machine learning model, because now your machine learning model is only taking 10 output, right? Previously model is taking 100 inputs. Now model is taking only 10 inputs. So you will get output very quickly, right?
So how many dimensions to be used in the model? It will be decided, pre-decided by us, as
Yes, yes, yes.
or it will be decided by the model.
No,
in
no.
the-
So we have to decide it first, right? Okay. Yes. Sometimes we also do the feature selection, right? Because not all features are relevant for learning the machine learning model, and sometimes if you use all features, it may also confuse the machine learning model, right? So let me give you one example. Let's say if you want to calculate the body mass index, and to calculate the body mass index, you are having several features. So, for example, age is one feature, gender is another feature, height is another feature, weight and eye color, right? So these are the features that are present in the data set, and our goal is to predict the calculate the body mass index. Now, as you can see, body mass index only depends on height and weight, right? So we don't need age, gender, and eye color features. So therefore, uh, we have to filter out age, gender, eye color when we are calculating body mass index, right? So therefore, depending upon our data set, depending upon our task, we may use the filter selection as a pre-processing techniques, and we may not use the filter selection as a pre-processing technique, right? Yes. And let's say if you are using if you are using the dimensional reduction also filter out unwanted features, right? So sometimes you can use dimensional reduction as a pre-processing techniques, using which you can select the relevant feature, most relevant features uh, for training the machine learning model, right? Okay, now let me discuss the types of features or types of output we may have. Yes, so features as well as output can be real valued, can be binary, can be categorical, can be ordinal, right? So real valued feature means when we are having real valued numbers, right? So for example, pixel intensity. Pixel can have values from 0 to 255. So therefore, it's a real valued features, right? House area again a real valued number, right? House price again a real valued number. Temperature, rainfall amount, right? So these are the cases, example of real valued features, right? Binary features means when we are only having two cases, right? Male or female, adult, non-adult, yes or no, right? Categorical feature means when we are having uh, finite choices, and we are any one from finite many choices, right? So for example, zip code is a categorical feature. Blood group is a categorical feature, right? O group, A group, B group, right? Okay, then we have the features. Ordinal features means when we are having categorical features, and there exists some order, right? So for example, in grades, A grade, B grade, C grade, so there we have order, right? So if we are having some order, then that type of feature is called the ordinal feature, right? Okay, so we may have real valued input, we may have the binary inputs, we may have the categorical input, we may have the ordinal input, right? Yes. So here in the same example, as you can see, uh, here we are having numerical feature also, we are having discrete feature also, we are having categorical feature also, we are having ordinal feature also, right? Okay, so let me first cover the performance measure, and then I will come back to the types of feature part, right? Okay. So if you want to calculate the performance of any machine learning model, then we need to first define the performance measure, right? And depending upon our task, we can select the performance measure, right? So for example, in regression case, either we can choose the square error, or we can choose the absolute error, right? Okay, so now let me take the same example. Here, suppose you want to predict the house price using house area, right? So here, what is my input? House area, right? And what is my output? House price. And here our goal is to establish relationship between house area and house price. And here we are doing regression problem. We are solving a regression problem, because given house area, we are predicting a uh, house price, real valued output we are predicting, right? So in this problem, we are solving a regression problem. Now it depends on us. We can either choose linear model to solve this problem, or we can choose the non-linear model. So suppose if you choose the linear model means we will use line, plane, or hyperplane to solve this problem, right? Okay. So these are the values, these are the points that we have in our data, in our training data, right? Okay. So here on x-axis we are having house area input, on and y-axis we are having output house value, right? So house value is the output, and here input is the house area, right? Okay. And these are the training data, right? And using these training data points, we will train a model to predict house value given house area, right? Okay. So since here we are solving a linear regression problem, so in this case we will learn a line, right? Okay. So let me ask one question. Can you give me example where we will learn a plane? So in this case we are learning a line, right?
When we have two features
Two
and
features, yeah, one output, right? So when we have two features and we are predicting one real valued output, in that case, we will have points in 3D, right? So let's say x-axis we are having one features, y-axis we are having another input. So x-axis we are having one input, y-axis we are having another input, and let's assume z-axis we are having output, right? So we are having points in 3D. So therefore we will learn now the plane, right? And let's say if you are having more than two input, then we will learn a hyperplane. Hyperplane means we are learning a linear in high dimensional space, right? So in 2D plane, sorry, line, in 3D plane, and in high dimensional space we will learn a hyperplane, right? Okay. So since here we are only having one input, so therefore if you are solving a linear regression, if you are using a linear regression model, then what actually we are doing, we are learning a line, right? And this is the line we want to learn, right? Okay. Now what is the equation of a line? Y is equal to mx plus c, right? Y is equal to mx plus c. So here y means the output. So house value output is equal to this W naught corresponds to the C value plus W1 times house area. House area means the input, right? So this is nothing but the equation of line, right? Yes. y is equal to mx plus c, right? So here this house area, you can think like input x and house price is nothing but the output y, right? Okay. So this is the model that we want to learn, right? Now in this case, what will happen if you change this the slope of this line? So what is this W1? W1 is one weight. W0 is another weight, right? And here model means these weights only, right? So this W1 is nothing but the slope, right? Y is equal to mx plus c. Here m is nothing but the slope and c is the intercept, right? So slope means this angle, right? So this angle is the slope, right? So if you change W1 value, the orientation of this line will change, right? Let's say if W1 is 0, which means now the orientation, so this line will become parallel to x-axis, right? Right? So if you change the value of the value of this parameter W1, the orientation of this line will change, right? So the orientation will change if you change the W value, right? If you change W0 value, this line will get shifted, right? So let's say here, if you draw the one line, here the angle is this, right? So W1 is nothing but the tan theta, right? In this case, what is W1? Tan theta, which is nothing but the slope of this line, and C is this intercept value, right? So if you change W1, this angle will change, right? Theta will change. So in other words, if you change W1, the angle will change, and finally the orientation of this line will get changed, right? If you change W0 value, this shifting will change, right? The C value will change because this distance is nothing but the C value, right? Okay. So here our goal is to learn this line, right? And when I say our goal is to learn line, which means we want to learn W0 and W1 value, optimal value for W0 and optimal value for W1, right? So here, what exactly we are learning? We are learning these two values, slope values and intercept value, right? Because if you change these two values, slope value and intercept value, the orientation of line will get changed, and the shifting of this line will get changed, right? It will get shifted if you change the C value, right? Okay. Any doubt in this example?
No, we are good. But do we do this for each feature? We will try to frame this for each, like this is house area. Now, if it is like some other feature, we'll do it for each feature, or is this just for an example that you showed us?
Yes. So good question. So here it depends on what type of model we are learning. We are learning linear model or non-linear model. So for example, if you only have one features, right? If assume you are only having X feature, X1 feature, in fact. Yes. So in case you only have one features, then you will learn Y is equal to M X1 plus C, right? Now, suppose you are having two features. So M is nothing but the W0 and W1. So let me write in W0 W1 form so that the notation will be consistent, right? So here y means the output, x means the input, right? So y is equal to w1 x1 plus w0, right? Or you can write w0 plus w1 x1. Y is equal to w0 plus w1 x1, right? Now suppose you are having two inputs x1 and x2, and if you are learning a linear model, then what ultimately you are learning? You are learning w0 plus w1 x1 plus w2 x2, right? And suppose if you are having three inputs x1, x2, x3, and you are having one input, right? So suppose inputs we are having three values x1, x2, and x3, and output we are having one real values y. And if you are learning a linear model, then what ultimately you are learning? Y is equal to w0 plus w1 x1 plus w2 x2 plus w3 x3, right? So this linear model we are learning if we are solving a linear regression, right? Now let's say if you are learning a non-linear model, then what we will learn? So it depends on what type of polynomial we are learning. If you are learning a quadratic polynomial, which means degree 2 polynomial, then in that case, if you are having two values x1 and x2, then you are learning a polynomial, right? So in that case, what model we are learning? Y is equal to, okay, so let me write. If you are using degree 2 polynomial, which means you are learning a non-linear model, and you are having two inputs x1 and x2 and one output y. In that case, you will learn y is equal to w0 w1 x1 square w2 x2 square plus w3 x1 x2, right? So we will make terms that is having degree of 2, right? And then w4 x1 w5 x2, right? So it depends on what type of model we are learning, right?
So what would be the W0? Can you please?
Yeah, so here W0 in ML terms is called bias term, right? So this is the bias term, and this W1 is the parameter that we are learning, right? And in fact, you can treat both W1 and W0 and W1 as the model parameters, right? Because here in this case, what we are learning? We are learning a linear model, right? And that linear model contains two parameters. In this case, the first parameter is W0 and the second parameter is the W, right? And if you change the value of these parameters, the model will get changed, right? Okay, so any other doubt here?
How to get into the value of this biased output? I mean, W0. How we can presume or like get to know the value of W0 in
W1.
all. Yeah.
Yes. So for that, we will use machine learning algorithms, right? So we will use machine learning algorithm, and depending upon the working of that machine learning algorithm, we will get the optimal value of W0, W1, right? So it in fact it's a optimization problem. We have to optimize something, and then the optimizer will give us the optimal value of W0 and W1, right? Okay, so before that, I want to cover the error part, right? Because let's say you want to get the optimal value of W0 and W1, then you have to first define the performance measure, right? Because what finally we want? We want the performance of our model to be higher or lower? So let's say
It should
if
be
we,
Higher, I think.
higher, yes. So which means the optimal value of W0, W1 is related to the performance of our model. If we want high performance, then some values exist for these parameters that will give us the high performance, right? So if we want to get the optimal value of these parameter values, optimal value of these parameters, then we need to first define the performance of model, right? Then only we can measure that these values are the best values, right? These values are the optimal values. Because if you use these values, then we will get the high performance, right? So this is the reason why we have to define performance measure so that we can measure how well our model is doing, right? How good is our model, right? So for that, in case of regression, we have several options. We can use the mean absolute error, we can use the mean square error, right? Okay. So suppose this is the line that we wish to obtain, we wish to learn, right? Okay, now suppose I don't know whether this is the optimal solution or not, but let's say this is one solution, right? This can be one solution uh, to fit a linear regression model over these data points, right? Now this solution can be the optimal solution, or this solution may not be the optimal, right? Okay. Now see these data points here. How many data points we are having? Total 5, right? First data point, second, third, fourth, and fifth, right? Now for each data points, we are having input and output, right? So for example, this first data points, we are having one input. So this is the input value, house area value, right? For this first data point, and this is the actual output value for this first data point, right? Because in data points, we are so here we are solving a supervised learning problem, right? Because supervision is available with us, right? So supervision means output value we already have, right? So for each and every input we are having output value, associated output value, because we are solving a supervised problem, right? So label is we are having, so here label means y value, output value, right? Okay, so actual output we are having for this first data points, and this output is the predicted output for first data points, right? So as you can see here, the model is telling that the output has to be this value, right? But the actual value is this value, right? So now we are having two types of value: actual output value and the values that our model is predicting, right? So what we can do, we can calculate error here, right? Now, depending upon whether how you are defining this error, either you can define predicted minus actual or actual minus predicted. It depends on you. So here, let's say if you are defining the predicted minus actual, so depending upon this value, some errors you will get some positive errors and you will get some negative errors, right? Because here, if you see this, if you calculate this difference is negative, but for the point 2, this difference is positive, right? If you calculate y hat value minus y1 value, you will get a negative number, right? Okay. So here we may get either positive error or negative error, right? So what is the meaning of getting error?
Uh, this I think we already know that means squared error, so that it should not cancel the positive and the negative errors. That is why we are going for a mean squared error. So
Okay, okay,
we
okay.
are right.
I think this portion has been already covered, right?
Yeah,
Okay,
this is covered by something.
okay, okay. So so what I can do, I can simply skip this part, right?
Yeah. And the optimal W0 and W1, to find that, we use the gradient descent approach. That has also been covered by something actually.
Okay, no problem. So I will skip this part, right? Okay, so that means we are having some positive negative error, so it will get cancelled out. So therefore, we are using squared error, right? Now this square error we have to optimize to get the optimal value of weight values, right? If we are using optimal weight values, optimal values for W0, optimal values for W1, then this quantity, this mean square error will get minimized, right? So now to get the optimal value of W0 and W1, we have to minimize this error, right? Now there can be several methods to do this optimization. Either you can use iterative method or you can use analytical method if possible, right? I'm not saying always analytical method we can use. Sometimes we can use analytical method, sometimes we cannot use analytical method, so we will go with the iterative method. So gradient descent is one such iterative methods, right? It iteratively solve problems, it iteratively minimize this error, and we will finally get the optimal value of W0 and W1. But this the same solution you can also get using least square solution, right? Least square method. So least square is an analytical method. You can make some mathematical equation, in solving those equations directly. You will get the solution, right? Okay. So now you are having two options. Either you can use iterative methods or you can use analytical method to get the optimal value of W0 and W1, right? So this way you can get the.
Can you explain what is the analytical method? I couldn't understand. Iterative method we understood, but what is the analytical method?
So analytical is not always possible. So here, what exactly we are doing? Here we are establishing a relationship between input and output, right? So for first point, you can write that relationship. Second, you can write relationship, and then you
Solving
can
the equation for each point.
equation of linear. Yes, y is equal to ax. So now you can do matrix inverse and you can get the values, right? Okay, but in machine learning, we will rarely use analytical methods, because here, since we have since we are dealing with the large number of features, so therefore, if you construct that matrix, if you do the inverse, then it will be very costly, right? Because we are dealing with 1,000 features. So if you use the analytical method, then you will construct a matrix of size 1,000 cross thousands, right? So it's a very big challenge to invert that 1,000 cross 1,000 matrix. So that's why in ML we prefer iterative methods, right?
Okay.
Yes. Okay. So here, if you fit a linear model over this data, how many linear model can fit this data? Infinite many, right? There can be infinite many lines, then can fit these data points, right? So here I'm showing three such possibilities. So let's say over these data points, either you can fit line A, line B, line C. Now question is, which line or which linear model you will choose, right? So line A you will choose, or line B you will choose, or line C you will choose. Or how can I choose? So here I'm having three options, three models I'm having. Line A means model 1, model 2, model 3, right? So which model I should choose here? I will choose a model that minimizes my error, right? Or minimizing error means maximizing performance, right? If we are minimizing error, which means the model we are maximizing the model performance, right? Okay. So here we will choose this line as our model, because if you use this line, this line minimizes our error or maximizes our performance, right? Okay.
Why do you use that root mean squared? Squared error we understand. What is the purpose of root mean squared?
Actually, we use squared error most of the time, right? Because even if you use the root square error, you will get the same value, right? Same solution you will get. Okay, so let me open that slide. Yes. Suppose you have the best value of W0, W1, right? Assume you are you got the optimal value of W0, W1. Now, if you compute mean square error, can I say that for optimal value of W0, W1, this error will be minimum? If you choose any other value for W0, W1, you will always get the higher error. Can I say this statement? Yes, right? Because if I use optimal value, best value of W0 and W1, then the error will be minimum, right? If you choose any other value other than the optimal value, you will always get the higher error, right? Now, even if you use the square root, the property will hold here also, right? For the optimal
It's
value,
just another measure that we use, right? That's it.
yes.
Oh.
In both cases, you will get the same values of W0, W1. So it's not like that if you put here under root and the solution will get changed. No, even if you put here the square root or you write you use this error mean square error as a error matrix, you will get the same values of W0, W1, right? Because in both cases, when you use the optimal value of W0, W1, this is also minimum and this is also minimum, right?
Okay.
And most of the time we will only use mean square error. We will not use square root because for numerical stabilities, because why I should calculate a square root, right? It will consume some time if I'm calculating square root, and if I'm getting the same solution, I will use this formula, right? Okay. Okay, so let me ask one interesting question. Here we are using squared error. Can I use here the absolute error? Absolute error means the mode of actual minus predicted, right? So this is our error. Either we can choose the squared error, or we can also choose the absolute error. Yi hat minus yi. So can I choose here the absolute error, mean absolute error, in place of squared error? Or let's say in what cases we should prefer uh, absolute error over squared error? Or in both cases we will get the same solution?
I think there is some problem in the absolute error. I don't remember. Sometimes Sandeep has told us.
Yes.
Yep.
See,
Small errors we can use root, and for large errors we can use the absolute value.
Actually, it depends on our data. So suppose if we are having outliers, if we are having noise in our data, then we should use the absolute error, right? Because if you are having any noise, if you are having any outlier, then for that outlier, the prediction will be wrong, totally wrong, right? Because the point is outlier, the point is noisy, so output will be very high, either very high or very low, right? Because that's why that point is the outlier. So here, if you use squared error, it will quantify that error, right? So for example, if this difference is let's say if this difference is 2, and if you use a squared error, it will make it 4, right? Because 2 square is 4, so it will quantify that error, right? So if you have if you have the noisy data, or let's say if you have outliers present in your data, then you will use the absolute error and not the squared, right?
So normally we'll be eliminating outliers during pre-processing phase.
Yes, yes.
But
But let's say
does it
yes, yes.
still make sense to use this combination?
If you are sure, 100% sure that you have filtered out all noises and outliers, then yes, you can use the squared error. But if you are not so sure, then you should try, or at least what you can do, you can try both options, and then you can pick the option that maximizes model performance, right? Because even if you pre-process your data, you cannot say that you have 100% removed all noises present in the data, right? It will filter out some noises, it will filter out some outliers, but we don't have any single method that can claim 100% I can clean this data, right? So there are some limitations. So it depends. So it's better to try both options, and then we can pick the option that maximizes our performance. Or let's say, uh, if you are not pre-processing your data, then in that case, uh, you must use the absolute error and not the squared error, right? And let's say, even if after pre-processing, if you are not getting the clean data, then we can use the absolute error, right? Okay.
Usually in machine learning, we use multiple performance metrics to arrive at the solution.
No. So it's
Like,
again a hyper parameter, right? Because the model optimization will depends on what type of loss function we are choosing, right? Because when you use the gradient descent method, what exactly the gradient descent method will do? It will optimize that error. It will minimize that error, right? So if you are using squared error, then in that case, the magnitude of error will be high, right? So it will penalize, it will find the value of weight unknown parameters W0, W1 in such a way that error can be minimized, right? Because you have already quantified that error by doing square, right? So which means you are penalizing HGD algorithm, you are penalizing your optimizer to get the value of W0, W1 in such a way that error can be reduced significantly, right? Now there can be cases. So for example, let's say if you have the outlier, and just because of that outlier or that noisy pixels, you are getting very high error. Model is correct, but you are getting the error high just because of outlier, right? So in that case, model you will end up getting the wrong solution, and that problem is called the overfitting, right? So overfitting has been already covered, or overfitting is not covered yet?
Know the
No.
concept, but does not been told.
Yeah, we covered it earlier, so but we can go over it again. But I have a question on the previous point.
Yes, yes.
When you say that this performance measure is a hyperparameter, so if we have got more than one performance measure, let's say absolute or mean squared error
Yes,
or
yes,
mean
yes.
squared, then how do we set these two? I'm saying, are we saying that both of them will be iterated over?
Independently we will use. So let's say first we will use the absolute error. The second time we will use the squared error. Now we have the two model. First model is using first model we are optimizing using absolute error. The second model we are optimizing using the squared error, right? Now what I will do, I will simply test my model performance, whether model 1 performance is greater than model 2 or not. Let's say if model 1 is outperforming model 2, then I will use model 1, else I will use the model 2, right?
But in this case, when we say the performance is different, right? Better, then our performance measure itself has changed. So how do we know which one is better?
No, we don't know. That's why we are calculating the model accuracy in both cases, right? So see, if you are dealing with very simple data, then you can visualize your data. You can visualize that yes, we have the noisy pixels, we have the outliers, and even after doing noise, after using pre-processing techniques to filter out noises, to filter out outliers, we can visualize our data because we are dealing with a simple data, right? Assume we are dealing with data set where we are having 100 inputs, or let's say 1000 input, we are having 1000 features we are having for each and every data point, right? Now how can I visualize 1000 dimensional data, right? I can only visualize 2D data or 3D data, but I cannot visualize 1000 dimensional data, right? So therefore it's very difficult to know how well the pre-processing techniques is doing, right? So
So how do we measure the accuracy of model?
we measure accuracy using test data set. So what we generally do, we
I
have
mean,
two types of.
what do we measure? But my understanding is that we were using those performance measures to determine the accuracy. But when you are saying that in the hyperparameter tuning, we change the performance measure itself, right? And when we are going to accuracy measurement, then how do we compare these two?
Yes, yes. So either you can calculate error, or you can calculate the accuracy, right? So for example, using test data, you can use test data to check model 1 error, and you can use model 2 using the same sets of data, right?
Yeah, that's what my question is, that when you were saying that when we check the accuracy, we are using a performance measure, right?
Okay, so that part I will cover after the break, because
Okay.
I have another, because if so this is again a different topic, right? Cross validation. So here we have to divide the data set into two parts: training and testing. So in broad sense, what you can understand here, one sets of data we will use to train our model, and one set of data we will use to check the performance, how good our model is doing, right? Because we already trained our model using training data, so we cannot say that this is the good model or this is the bad model, right? Because we have already used their data, model has already seen their data. So therefore, while evaluating the performance of any model, we will use the data points that we are not using in training part, right? Because why are we building these machine learning models? Are we building these machine learning models to perform well on the past data or on the future data?
Yeah, if you plan to cover it later, that's fine. So my question was that when we are measuring accuracy and if you're using the same measure that
Yes.
we had changed, right? Then how do we?
No. Yes, so we will use the same measure over future data. The data points that model have not seen in learning those
Yeah,
optimal
that's
value of
clear.
hyperparameter, right?
Yeah, that's clear. So
Yes.
we are talking only over test data, but you said look in hyperparameter first use, let's say mean squared error, and then you say root mean squared error.
Yes,
Now
yes.
the performance
So
measure itself has changed.
yes. So we can do now, we have two models. Model one is using absolute error. Model two is using squared error, right? So what we can do, we can again calculate absolute error for model one using test data, and we can calculate model two error using test data. And if let's say, or in other words, what you can do, you can calculate the accuracy. Now accuracy depends on the uh, the type of problem you are solving. Suppose you are doing a classification problem. In that case, and let's say if you are doing a binary classification problem. So here accuracy means how many times model is correctly classified, right? So you can use those measures, accuracy measures, to decide model one is better or model two is better, right?
Yeah, classification is simpler, but in case of regression, we will still need to define some performance measure, right?
Yeah. So in case of regression, we can use yes, we can use a root mean square error, or we can use squared error, or we can use the absolute error, right? But not on the training data. We will test these errors using test data, using future data, because we are building these models to predict some values in the future, not in the past, right? Because past data we already have. So why would I train a machine learning model to predict output
No, that part is
in
clear.
past
We
data,
are only
right?
talking about test data here.
Yes.
My question was that you are saying that we can use it as a hyperparameter. So in the first model, we use a different measure. In the second model, we used a different measure. And when we are comparing accuracy, then we again need a performance measure. But the performance measure itself has changed. So how do we compare these two models?
We can compare using test data.
Yeah, for
Let's
test
say,
data, what do we measure again? But how do we say this model is better?
so if model one is better, then you will get the lower squared error, mean square error, right?
But in the two examples, right, we have changed the performance measure itself. If let's say the performance measure was the same, we can
But in
compare
case
it.
of best model, you will get mean square error lower, and also mean absolute error will be lower. So it's not like that for the best model you will get the absolute error high and the squared error low, or squared error low and absolute error high, right? You are getting here difficulty because your training data is not perfect. In training data you are having some outlier, right? In training data you are having some noises, so that noise or that outlier is creating problem, right? But for the best model over the test data or the future data, mean square error will be low, and at the same time absolute error will also be low, right?
So we have to run both the models on both the measures then, right?
So either you can use the absolute or you can use the squared. It doesn't matter, right?
Okay,
We are
maybe we
only
can talk
here.
more about it when we cover the accuracy part.
Yes. So here, what point I'm here trying to explain that when you are dealing with outliers, when you are dealing with errors, we must use the absolute error and not the squared error, because if you use the squared error, the error will get magnified, right? Now what effect it will create if you magnify that error. You can here explain this fact using overfitting phenomena, right? Which means you are fitting your model too rigorously over noisy points, right? So let me ask one question. Suppose you are having noisy data, or suppose you are having outlier model. Do you want your model to fit perfectly over noisy data, or you want to skip those data points?
We'd like to skip them.
Yes.
So that even if it doesn't fit those outliers, it's okay.
Yes, exactly. But now you are forcing your model to fit those outlier points if you are using scared error, right? Because for outlier points, for noisy points, the scared value will be very, very high, right? Because let's say if a point is outlier, point is noisy. What do I mean by noisy? Noisy means very high value or either very low value. So when you have very high value or very low value, the difference will be very high. And if you scare that difference, it will you are magnifying that quantity, which means you are penalizing your model in such a way. You are forcing your model to fit those outlier points, those noisy points, right? Which means uh, you are pushing your model to the overfitting condition, right? Are you getting my point?
Yeah, that part is clear. We had
Yes,
covered.
yes. So this is the reason why when we have the noisy points or the outlier data points, when we have the noise present in our data set, then we always prefer absolute error over squared error, right? Okay, so this overfitting I will cover after the break, right? So let's take a 5-minute break, and then I will start from the slides, right?
Hello? Hello? Anyone able to hear?
It's break time.
It's break time, 5 minute break.
Okay. Can you hear me?
Yes.
Okay. Okay, so now let me briefly discuss the overfitting concept. So overfitting means we are doing perfectly, we are doing very good on the training data, but we are not doing good on the test data, right? On the future data, which means model is memorizing the training data, right? Model is memorizing everything, which is not good when we train a ML model, right? So here, let me take one example. Suppose here we are doing this classification problem. We are solving this binary classification problem where color represents the class, right? So we are having two types of data points: blue class data points and red class data points, right? Now, as you can see here, if you see these data points carefully, uh, we are having here several outliers, right? So, for example, this point is an outlier, right? This point has to be a red point, but in our data point, we are having this point as label blue, right? So this point is an outlier. Again, this point is an outlier, uh, and yes, this point is the outlier, right? So here, when you train your model, when you are having outliers in your data set, noise present in if you are having noise in your data set, right? Now, now, then in that cases, how can we train our machine learning model efficiently? So we can train model efficiently. We can get the correct machine learning model even if we are having outlier, or even if we are having noise in our data sets. But then we have to prevent overfitting, right? Now there are several ways using which we can prevent overfitting. Okay, so now let me discuss this example. So here, suppose if you want to solve this binary classification problem, which model I should choose here? I should choose the linear model or non-linear model? Can I use a linear model to separate out these data points in two classes?
No.
No, we have to use some non-linear model. Then only we can separate out these data points into two different classes, right? Now, it's not like that we can use any non-linear model, right? Or in other words, we have to first identify the correct degree or correct degree of polynomial, right? We have to here fit a non-linear model. But with what degree? Degree 2, degree 3, degree 4, degree 5, right? We can fit here several nonlinear models, right? Okay, so here I'm showing two nonlinear models. One nonlinear model is this black model, and other one is the green model. So in this case, which model you will choose? The black model or the green model?
Black.
Black. Okay. If you choose here the green model, can you tell me the accuracy of green model over this training data? What is the accuracy of green model over this training data?
100%.
100%.
Accuracy will be
Here,
high.
yes. So training is in fact 100%. You are getting 100% accuracy. If you use green model, you can even classify each and every points, training points, right?
Yeah.
But then also we will not use green model, because we are forcing our model to fit the noisy data points, the outlier data points, right?
Right.
So this is why we will use the black model and not the green model, right? Okay, now let's say if you use the black model, what benefit you will get?
perform better in the real world scenario.
Yes, yes. But here, one point you can note here, if you choose the black model, the training accuracy is not 100%.
Okay, test. Yes, the test accuracy maybe.
Yes, yes. So which means we also care training accuracy and we also care the test accuracy, right? Okay. Let's say you are learning a model and the training accuracy is very, very poor. So should you use that model or you will not use that model?
I mean,
Should
we
I
go
use
by
that?
the test accuracy, not by training accuracy.
Sorry, can you repeat?
I'm saying we should only be looking at the test accuracy, not the training accuracy.
No. Here I want to clear one important point that test accuracy also matters, right? If sorry, the training accuracy also matters, right? If training accuracy is very, very low, very, very low means let's say 10% training accuracy, 20% training accuracy, which means model is not learning anything. Model is not able to learn the underlying pattern, underlying the trend present in the data, isn't it? Right? So here, if you calculate the training accuracy for green model and training accuracy for the black model, so maybe the in case of green model, you may get the 100% accuracy, 100% training accuracy, and if you use this black model, so maybe you may end up getting, let's say, 97% training accuracy or 98%. So 97, 98 is again a good number, right? I'm saying if training accuracy is, let's say, only 20%, 30%, 40%, or let's say 50%, then it matters, right? If training accuracy is very, very less, which means model is not able to learning from data, right? Now, there can be several reasons for this. One reason can be you are using wrong model. Model is not correct. So, for example, in this case, if you use linear model, what training accuracy you can achieve? What best training accuracy you can achieve if for the same data set if you use the linear model? Training accuracy will be very, very poor if you use linear model to solve this for this data set, right? Because you are using the wrong model. For this data set, you should use the non-linear model and you are using the linear model, right? So here, overfitting means you are getting very high training accuracy, but very poor test accuracy, right? So training error, or I don't want to confuse you. So let's talk in terms of accuracy, but both are same. Either you can say maximum accuracy or you can say the minimum error. Both are equivalent, right? So let's in terms of accuracy, let's talk in terms of accuracy, right? So in case of overfitting, the training accuracy will be high, but at the same time, test accuracy will be poor, right? And what if the training accuracy is poor? Then in that case, we will change our model, right? Maybe we are using wrong model to solve that problem, right? So overfitting is one phenomena. Another phenomena is underfitting. So has underfitting topic has been covered or not?
Yes.
Okay. So we have to prevent overfitting. At the same time, we have also prevent underfitting. So overfitting means training accuracy is high, but test accuracy is poor. Overfitting means training accuracy is high and test accuracy is poor. Underfitting means both training and test accuracies are poor. Training accuracy is poor, and at the same time, the test accuracies are also poor, right? So if model is suffering from underfitting problem, which means either we are using wrong model or we have to tune that model, right? We are not tuning that model. So maybe we are using some wrong values of hyperparameters. In that case also the underfitting may happen, right? And in fact there can be several reasons for underfitting and overfitting, right? Okay.
So are there any techniques to understand what degree of polynomial we should be starting with?
Yes, so yes, we do have techniques and using cross validation we can get the model. And in fact in cross validation what we do, uh, we will try out several models and we will pick the model that maximizes the test accuracy or the validation set accuracy, right? But before training model we cannot say anything, right?
Can the data insights help us understand?
Yes, exactly. Data insight can also help us when we are dealing with the low dimensional data, right? When we are only having 2D data, 3D data, then definitely we can by visualizing data we can do this. But when we are dealing with the 1000-dimensional data, then we cannot do anything, right? We have to try out multiple options, then only we can say anything about the optimal model, right? Okay, so let me briefly cover the hyperparameter. So is this topic already covered, hyperparameter selection, or not?
No.
Okay.
No.
Yes. So sometimes we do have several choices, several options we have, right? So for example, either we can take model one or we can take model two, or maybe we are having 5 models out of which we have to select the best model, right? Or maybe we are having uh, some options, right? So option one, option two, option three. So we have to choose one options. That option can be the loss matrix, right? So loss we can choose, let's say absolute error, or we can choose the squared error, right? So now to resolve those cases, we in ML machine learning terms we use the cross validation, right? So cross validation we can use model selection to select the most model, the best model. We can use the cross validation technique. We can also use cross validation technique to select the correct value of hyperparameters. So hyperparameters are the parameters on which the model performance depends, right? So there are two types of parameters. First type of parameter are the model parameters, and the second type of parameters are called the hyperparameters. So hyperparameters are not the model parameters. Hyperparameters are the parameters on which the model performance depends, right? So for example, the the choice of loss function, right? So choice of loss function is a hyperparameter. Either you can take the absolute error or you can take the scared error. Now that 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 option you can explore using uh, cross validation. So in cross validation, what we'll simply do, we will train both models and we will pick the model that maximizes our performance, right? Okay. So now here the question is, while checking model performance, can we use the training data? No, we cannot use the train data because we are building these models to predict something in future, right? We are making these models for the future data and not for the past data. Using past data, we will train these models. And what is our end goal? Our goal is to predict something in the future, right? Now it depends on our task. If we are solving a classification problem, the model can predict the category. If we are solving a regression problem, model can predict the real value output, right? Okay, so this is the reason why we will not test the performance of our model, any machine learning model, over the training data, because training data we have already used in building that model, right? So therefore, what we generally do, we split our data into multiple parts, right? We split our data into multiple parts. So assume we are having 1,000 data points. So what I can do, I can split 1,000 data points into, let's say, two parts. 80%, let's say, data points belongs to first part, and the remaining 20% may belongs to the second part. Now the second part I will use as a proxy for future data, and the 80% data I will use to train our machine learning model, right? And this is called the splitting of data, right? We are splitting our data set into two parts: training set and the test set, right? The training set we will use to train our model, and the test set we will use as a proxy for the future data. So we will test the model performance only over the test data, right? Because we are using this test data as a proxy for the future data, right? Because we are building our model for the future data, right? And this data we have not used in building our model. So if our model is performing good over this test data, then what we can say that model will also perform good over for the future data, right? Any doubt here? Right?
So this training data itself we are dividing into two, right?
Yes, yes.
That is for hyperparameter tuning.
Yes, yes. Because here the problem is future data we will get in the future, right? So, and we cannot wait. So therefore, what we can do, we can divide whatever data points we are having in two parts, right? First part we will use to train our model. The other part we will use to test the performance of any machine learning model. And since we are not using these data points in building our model, so therefore we can think we can assume if our model is performing well over test set, which means model will also do better in for the future data, right? Okay. Now here the question is, how can we divide data points into two parts? So here the answer is we will do this partition randomly. We will randomly divide data points into two parts: training set and test set, right? Yes. So we will randomly divide training set and test set, and sometimes we also divide uh, training data into three sets: training set, validation set, and test set, right? So this test set we will reserve to check the performance of any machine learning model. This validation set you can use to tune the hyperparameters of the model, right? And this set you will use to train your model, right? So sometimes we split data points in two parts, training and test, and sometimes we split the data points in three parts, training part, validation part, and the test part. So this validation set we will need if we want to tune hyperparameter, right? But let's say if you do not have any hyperparameter, then there is no need to split training data points into three parts, and you can split in two parts, training and test, right? But if you have hyperparameters and if you want to know the correct value of hyperparameters, then it is always a good idea to split data points into three parts: training, validation, and test. The test part you will only reserve to test the performance of your model, and this test part, this test set, you will consider as a proxy for the future data. This part you will use to train your model, and this validation part, validation set, you will use to measure the performance of any machine learning model to get the optimal value of hyperparameter. So for example, let's say now you have to decide, should I choose the absolute error or a scared error? So what you can do, you can train your model 1 using absolute error over this training data point, and model 2 using the same data points. And now what you can do, you can test model 1 over validation set and model 2 over validation set, right? Now whichever model is giving the best performance, you can take them, right? Okay. Okay, so is there any problem in this if you do this random splitting?
If let's say we get the test data which is sorted, let's say based on prices, then what can we do to randomize it?
Sorry, can you repeat?
Let's say the test data that we have for the example that we're talking about for housing prices, the data is that we get is sorted on, let's say, housing prices. So what can we do to randomize it so that, for example, if it's just split it 70-30, then it may be more kind of.
No. So what we can do, we can select data points randomly, right? So for a house price prediction problem, we are having nearly 20,000 data points, right? So what you can do, you can randomly choose any data points, right? So first data point can be any number between 1 and 20,000, right? So
Okay.
likewise, you can select data points randomly. But here the problem is, even if you select data points randomly, it may create some problem sometimes, right? So see here, what type of problem we are solving? We are solving a classification problem because we are having data points belonging to class 1 and some data points belonging to the class 2, right? Green class and the red class, right? Okay. So here, let's say if this the distribution, if this train and test distribution, let's say if mismatch, then it may affect the learning of any machine learning model, right? So let's say if you have skewed data means let's say 95% of point belongs to the class 1 and only 5% of data points belongs to the class 2, right? And since here you are doing random split, it may happen that after doing random split in this training data, you end up getting 99.9% of data points belonging to class 1 and very few data points you are having for class 2, right? Now, since in this training data, you are having very few data points belonging to the red class or the minority class, the model will not be able to learn the pattern present in the red class, right? Because you are having very few examples for the red class, right? So then it can create the problem, right? Because if you do this splitting randomly, the chances are very less, but yes, it may happen, right? Even if you have, let's say, even if you are having, let's say, 70% data belonging to class 1 and 30% of data belonging to the red class, right? As you can see here, if you do this random splitting, it may happen that after doing this random splitting, let's say 90% of example belonging to green class and only 10% data belonging to the red class, right? It is possible, because if you are doing, if you are selecting randomly, it can be possible, right? So then it will affect the model learning process, right? Because now we do not have the sufficient number of training example for that particular class to capture the underlying pattern present in that class, right? Okay. So this is the problem in random splitting. Can you suggest some solution to overcome this issue?
Some data sampling techniques.
Yes, we can also use some data sampling techniques. The other options is, what we can do. We can do this split multiple times, right? And then we can calculate the average model performance, right? So, for example, let's say you are having, initially you are having some data points, and you have divided data points into two parts, training part and the test part. You will use this data to train your model, and you will test the model performance using the test data, right? So this is one iteration, right? What you can do, you can repeat this iteration multiple times, right? So let's say first time you will use this data to train your model, you will use this data to test your model, right? Here we are doing random splitting. You will again repeat the same process. Again, you will do the random splitting. Now you will use this set as a training data and this set as a test data. Again, you will repeat this process. Third time, again, you will do the random splitting. Now, in this case, you will use this set as a training data and this is a test data. And finally, what you will do, if let's say if you are repeating this process 3 times, you will calculate average model performance, right? So let's say here you are getting some performance, model 1, for model 1 you are getting some performance. For the same model you are getting here some performance, for the same model you are getting some performance. So you will calculate here the average performance, right? Okay. Now this scheme is called the multi-fold cross validation, right? Because here we are splitting data set multiple times, right? Split 1, split 2, split 3. So this approach is called the multi-fold cross validation. Especially this in this example, what exactly we are doing? We are using three-fold cross validation. Three-fold means we are splitting 3 times, right? Okay. Any doubt in multi-fold cross validation?
But that data set is same, right? Whatever the data you got initially, you are just splitting them into 3
Randomly,
different.
yes, 3 different times, right?
Right.
And by calculating model performance over test data, now we can get the model performance, right?
But will it impact if I'll randomly splitting a data like 30 30 30 or maybe 20 30 40 or whatever, or should be randomly split into a equal number so that we can ensure that whatever data we passing to the model in a equal proportions, will that impact kind of performance or accuracy?
Yes. Actually, here the problem is data points are already imbalanced, right? As you can see here,
Yeah.
we are having more number of data points belonging to class 1 and the less number of points belonging to the class 2. And if you apply here the random splitting, this skewness may increase or may decrease because you are following a random procedure, right? So that's why here we are splitting it multiple times. But yes, you can also ensure that let's say if you a priori know that 70% of data I am having class 1 and 30% of data I am having class 2, then what you can do here, you can after splitting, you can ensure that in the training data 70% belongs to the class 1 and the 30% belongs to the class 2, right? You can do that. Okay, so there are two options. Either you can ensure, let's say 70% belongs to class 1 or 30% of class 2, and the other option is this multi-fold cross validation. So which option do you prefer? The multi-fold cross validation or the options that you are suggesting?
If we are able to do the first one, then that will be less costly, but it may not be feasible if.
Okay, so what are the
multiple
disadvantage if I use the if I fix this, let's say 70% belongs to class 2, 30% belongs to class 2. Okay, so let me discuss one case. See, we may have noisy data, we may have outlier present in our data, right? So if you do this splitting multiple times, sometimes we may have outliers in this set, sometimes we may not have the same outlier in this set, right? So therefore, this way you are getting a averaged model. You are getting, because some error will get cancelled out, right? Because now you cannot say that each and every time you will get the same outlier in this set, right? Are you getting my point? So this is why in ML people use cross validation over other schemes. So for example, even here you can ensure that, let's say if 70% belongs to class 1, 30% belongs to class 2. Here in this split also you can ensure that condition. You will choose here randomly, but in that random 70% must belongs to class 1, 30% must belong to class 2, right? But still you will not use this scheme, and in fact you will use this cross validation, because here this cross validation offer some other advantage, right? So for example, overfitting, it will overfitting, underfitting. So it, you will also get benefit, right? Because if you are splitting this time randomly, then sometimes in this split you may get the noisy pixel, you may get the uh, outlier data points, right? But in some splits you may outliers will not be there, right? So but yes, one drawback is there. This no, you have to train models multiple times, so it's very time consuming, right? But then again, I want to add one thing. We are training these models to predict something in future, right? So training is a one-time job, but testing or prediction at the future is a recurrent job that we do frequently, right? So even if we are spending more time while training our model, we can afford that, right? If let's say it, if you use the threefold cross validation, it will increase the training cost 3 times, right? I totally agree with that. But if you use three fold cross validation, the model that you will get using this approach is much better than the model that you got by fixing these values, right? Isn't it? So therefore, people generally use cross validation, right? Because training we are doing only one time, the testing we will do uh, again and again for the future data, right? Any other question?
So first we divide the data into train and test, and then we divide the train data into this training data and validation data?
Data,
Like
if yes, if we
right.
want to tune the hyperparameters.
Oh,
But let's say if we do not have the hyperparameters, then we will only split the data points into two parts, training and test, right? Because here we are reducing the number of training data, right? Because the model performance, machine learning model performance depends on the number of data points, right? If we have the limited data, the performance will be poor, right? So sometimes what people will do, uh, they do this three splitting scheme, training, validation, and test, and then they can tune, they can know the correct value of hyperparameter. So suppose, let's say, by dividing data points into three types, three sets, now you know that the absolute error is a better option over the squared error, right? So now you know that for this particular data set, absolute is best. So now what you can do, you can again divide data sets into two parts, and then you can only proceed with the absolute error, right? Because now I know the correct value of hyperparameter value, right? So why I should now split the data points into three parts, right? Because if I split data points into the three parts, then ultimately I'm reducing, I'm minimizing the number of training data points, right? And this is why people generally divides training and testing in 80 versus 80-20 ratio, right? So 80% we will use for training and 20% we will use for testing, right? Okay.
Generally speaking, we'll always have some hyperparameters. Is that correct?
Yes,
In real
we
world
always
problem.
have some hyperparameter. So the best approach is, initially we will divide in three parts, and once I know the correct value of hyperparameters, now I will train my model over the two parts, train and test. So I will use the complete train data, right? Because validation, how I am getting the validation data, validation set, I'm getting validation set from training data sets only, right? See, initially I'm having two sets, training set and test set. To get this validation set, I'm again splitting training sets into two parts, actual training set and the validation set, right? So in other words, I'm reducing the number of data points for the training, right? Okay, I think I'm not shared this slide, so maybe I should first share this slide in the chat section. Yes, so please download cross validation slide.
Where did you put it? In WhatsApp or in?
No, in chat option.
Oh, okay. Now I can see it. Yeah.
Mhm.
Can this also go in the WhatsApp so others who are not here can also download?
Okay, so maybe what I can do, I can share this slide with Gajendra, and maybe he can share with you over WhatsApp.
Yep.
I
Okay.
think maybe if any one of you can share in that group, please do that, right? Because I don't have access to that group, right?
Can you please also put that data pre-processing slide?
Yeah, so data pre-processing slide I have already shared yesterday, but if you want, I can share it again. Yes, so I have shared. Please download. Okay, so this part I have already covered, right? So the variable can be numerical, can be categorical, right? So numerical means having real valued values, right? Now the numerical can be further divided into two parts: continuous and discrete. So continuous means there can be infinite many values, right? So for example, let's say if you are having a continuous variable, then continuous variable can have, let's say, from 1 to 2, from 1 to 2 we can have infinite many values: 1.1, 1.111, 1.1111, 1.011, right? So there can be infinite many possible values if we are having continuous variable. So for example, house price is a continuous variable, right? Because house price can have infinite many values, right? Now, in case of discrete, we have finite choices. So, for example, age, right? So, age can have any value between, let's say, 0 to, let's say, 120, right? Or you can think 150, 0 to 150, right? Can have any value between their range. So, now we are having finite options, right? 0 to 150. So if we are having such type of variable, then that variable is called the discrete variable, right? So numerical variable, we can divide it in two parts: continuous and discrete. In discrete, we are having finite options. In continuous, we are having infinite many choices, infinite many values it can take, right? Okay. Now, the categorical means where we are having categories. So, for example, blood group. Blood group can be O, A, B, and grades can be A grade, B grade, C grade, right? So, these types of variable are called the categorical. And in fact, categorical we can divide into two parts: regular categorical and ordinal. So, in ordinal, when we have ordering, then that variable is called the ordinal variable, right? So, for example, grades: A grade, B grade, C grade. So, there exists an order, right? A grade is higher than B grade, B grade is higher than C grade. So, it's an example of ordinal, uh, right? Okay. Can you give me example of regular categorical?
Cat and dog.
Yes, yes. So if you are having a cat and dog type of label, then yes, because uh, we don't have any order in that, right? Or let's say uh, when you are recommending something, right? So positive recommendation, negative recommendation, then also we do not have any order in that, right? So that type of features or variables you can think is a regular category, right? Or on ordinal we are having uh, order, right? And I think I have already given the example in this slide. Yes, yes. So here ordinal means grade A, B, C in a course, because A grade is higher than B, B is higher than C. Category means blood group, zip code. These are the example of categorical, right? Okay. So in our case, or in for all these feature values, for all these inputs, we are having numerical values, and for ocean proximity, we are having categorical values, right? Yes. Okay. So next session, I will start random process, and then I will cover. So I think this part is already covered or not? Probability distribution.
No.
Okay. Okay. Okay, so maybe I can start from this slide next time, random process, right?
Okay.
And yes, I have already shared slides, so please download from the chat section, right?
Ravindra, just to ask. Now onwards, Sandeep will not be taking the session. You will be taking.
No, some topics I will cover and then Sandeep will take. Okay, so thank you very much
Thank you.
for joining.
Thanks.